This is Professor Pelton. This is Trigonometry, Chapter 3, Section 4, Vectors. This is Part 3 of 3. So previously we were finding vectors using coordinates. So basically given two locations, a start and an end, you could find the vector. However, you're not always given the start and end, you're given a magnitude and a direction, which is where the trig versions of vectors are going to come in. Okay, so given some magnitude in some direction, which typically will be bearings in this class, we can find the vector. So here's the original formula here that we've been working with, a plus bj, where you add the ck if you're doing in 3 dimensions. So if you drew the triangle here, okay, where there is your A side and there is your B side. So if I did my sine and cosine values, I would get these over here. And if I multiply by the magnitude on both sides, that would cancel over here. So A would become the magnitude times the cosine. And over here, it would be the magnitude times the sine. So we can take our original formula and swap out the A and the B now for magnitude times the trig function. So A becomes the magnitude times cosine of I plus the magnitude times the sine for j. So we replaced A and B with these A and B's. Okay, that's essentially what we did. So there are two formulas that are equivalent. So based on if you have two locations, you use the A and the B formula we used before. If you have a magnitude and direction, use this formula. So we're going to start with velocity vectors first. Okay, so wind blows 20 miles per hour, so that is our magnitude. Put that in our picture here, and it's north by 30 west. So if I draw north by 30 west, that means my actual angle is 120 degrees, because the trig angle and the bearing angle are two completely different things. They're related, but you can't use one of the formulas. So if I use the formula, v for the vector equals the magnitude times the cosine of the angle, I, plus the magnitude times the sine of the angle, j, will give us our vector. Since we do not know this beginning and the end, all we know is the magnitude and the direction. That's all we know. Okay, so the magnitude is 20 here, so 20 times cosine, and 20 times sine. And of course, we do not use bearing in this, use the trig angle, which is 120. So 120, 120. So we need the values of those now. So this coordinate here, all right, is a 60-degree angle. Right? Let me do that again here. That angle is 60 degrees. Right? So that coordinate right there is negative 1/2 root 3 over 2, correct? That's my cosine sine. So velocity equals 20 times negative 1/2 I, and 20 times root 3 over 2 j. So the velocity equals negative 10 I plus 10 root 3 j. So there is our vector. So whether you're given two locations or a magnitude and direction, you can find out the vector equation either way now, using either of the formulas. So the formula from this section or the formula from the previous section. Okay, pause the video, try the student problem. So a jet stream blows 60 miles per hour in a north by 45 degrees east. So if I do that, that's north by 45 degrees east, and that's a 60 mile per hour wind. So that also gives me an angle here, which also happens to be 45 degrees in this case. So therefore, the vector is the magnitude times the cosine of the trig angle, I, plus the magnitude times the sine of the trig angle J. And the 45 degree one's very nice. That coordinate is root 2 over 2, root 2 over 2. So I have 60 times root 2 over 2I, and 60 times root 2 over 2J. So we have 30 root 2I, and 30 root 2J is our vector for that jet stream wind. Okay, let's go to page 27. So we did velocity vectors. Next we're going to do force vectors, and force is a push or a pull in a direction. So just for explanation's sake, so you have a person here holding up a box, and gravity's pushing down the box. So you're holding the box perfectly still in space. Well, not in space, but in somewhere, some three-dimensional space on Earth. So what is the resultant vector, okay, for the box? Well, if the box is not moving, that means it's not going in a direction. And the vector going up and the vector going down are of the same length, because you are pushing up with the same force that the gravity is pushing down, so the sum is 0. So therefore you get the 0 vector as a result. So the vector here is in fact going to be 0I plus 0J, otherwise known as the bold 0 vector. Okay? Alright. Let's do another example problem. So you have two forces, just generic forces here. Usually they'll be like wind, or two boats pushing on something, or two tow trucks pulling, something like that in the book problems. But here, just kind of generic forces, F1 and F2. So one has 10 pounds, one has 30 pounds. One is north by 20 east, one is north by 65 east. And I've drawn the corresponding problems in the diagram to the left. So we need the formula for the first force and the formula for the second force. So the first force is 10, and the second force is 30. So that's the cosine of the angle I plus, same magnitudes again, the sine of the angle J. Okay, so now it's a matter of what are the angles. Well, if we look here, the first one was north by 20 degrees east, but that is our theta right here, not the 20. 20 is the bearing. Therefore, our angle is 70 degrees. Okay, and the next one was north by 65, so therefore our theta is the remaining angle, which is 25 degrees. So our resulting force vector is, in fact, F1 plus F2. So we have to add them up. So basically we have to do 10 times the cosine of 70 degrees plus 10 times the sine of 70 degrees plus 30 times the cosine of 25 degrees plus 30 times the sine of 25 degrees. So use your calculator. We forgot our i's and j's here. I, j, j. For a final resultant vector of FR is approximately 30.6 I plus 22.1 j. So that is our resultant vector. Okay, so the two things that we want are the magnitude and we want the direction. Okay. Alright, so we use the first diagram to figure out the angles, because again, the bearing angles and the trigonometric angles are not the same. Very rarely are they the same. In the previous case, we had one that was 45-45 because it split evenly, but here it is not the case. Okay, so next time we want to answer these two questions, I want to erase it. You can move down on yours, and we'll figure out what the case may be here. Okay. So, we have a resultant vector of 30.6i plus 22.1j. And the two things we want are the magnitude and the direction. Well, I drew this over here. This is the little bit better rounding on this. But we want to figure out the resultant, right? So that's the Pythagorean theorem or distance formula, which is the same thing, right? So the resultant magnitude is 30.6 squared plus 22.1 squared. I'll keep the numbers from my problem, not the diagram. That's how I rounded. So I get approximately 37.75 pounds. Okay, so that's our first answer. So the direction is this angle here, when you get this angle. Well, if we do this angle, I have opposite and adjacent. That's a tangent, correct? So tangent of theta is 22.1 over the 30.6. So if I inverse tan both sides, I get tangent is equal to inverse tan of 22.1 over 30.6. So my theta is approximately 35.84 degrees. Okay. So 35.84 degrees. However, that's not my bearing. That's my bearing. Okay? So I have to do 90 minus their 35.84 degrees. So that'll give me 54.16 degrees for that angle there. Because again, bearing and the trig angle are not the same. So therefore I'm going north by 54.16 degrees east. So that is my direction. Pause the video, try the student problem. Okay, for the student problem, again, we have two forces, force 1 and force 2. Force 1 is 30 pounds, force 2 is 60 pounds. So we have cosine of an angle, I, and then 30 and 60 again, sine of an angle. Okay, now we'll figure out our angles. So the first one is north by 10 degrees east, so it's a little sliver there. It's probably a little bit too much. If that's 10 degrees, then the remainder is 80 degrees. The bearing's 10, the trig angle is 80. So 80 degrees, 80 degrees. The next one is north by 60. So north by 60 will be right there, 60 degrees, which means my actual theta for the angle is 30 degrees. So 30 degrees, 30 degrees. So to get my resultant vector, I have to add f1 plus f2. So my resultant vector, after I plug them into the calculator, so I add these together to get the I. I'm going to get 57.2i. Add these to get the j's, j, 59.5j. So the two things we want are the magnitude and the direction. Okay, so let's take a second, move this down, and find those things. Okay, so if my vector is 57.2i plus 59.5j, then I have a triangle that looks like this essentially. 57.2 and 59.5. So that is my magnitude there. So using the distance formula, which is Pythagorean theorem, the resultant is the square root of 57.2 squared plus 59.5 squared. So my magnitude result is approximately 82.5 pounds. And if I want to find the angle here, I have to use tangent. So that is the tangent of theta equals 59.5 over 57.2. So if I tangent both sides inverse, tan inverse of tan and tan inverse of the ratio, that'll cancel. So theta will give me approximately 46 degrees. Okay. However, that's 46 degrees, which is the trig angle. That is my bearing, which is 44, because it comes up to 90. So I'm in fact going north by 44 degrees east is my direction. Okay, and that is the end of part 2, other than the concept. So the concept here is I have a force 1 vector that goes about 10 degrees. That's pretty high, 10 degrees, and that's my F1. Right? So that starts here. And then I have another one that's 60. That's right, it's 30, not 10. 30. The other one is 60. Okay, and that's my F2, I guess. And that's where it ends, and this is where it starts. So if I connect those, that is my FR, or the F1 plus F2 as a result. So this vector right here, its equation is right here. That's its direction, and that's its magnitude. So that's the concept of it.